Well, thank you very much for everyone for being here. My topic is architectural UHPC. If you don't know where you are, you're in the hot topics part 3 of 3 for ultra high performance concrete, sponsored by Committee 239 and others. So my background is I'm fairly new with Ceentek. I've got 30 plus years in the construction and material supply industries. I'm a longtime ACI member. And in my new position, I'm a precast manager. And with Ceentek, and our claim to fame is basically next generation UHPC 2.0, which is essentially nanotechnology using new nanotechnologies to improve UHPC, and of course our goal is to share that technology and to try to help folks develop their own UHPCs using our materials. So architectural UHPC is truly ultra high performance concrete. So just like any ultra high performance concrete, the big key is, of course, our strain behavior. And ACI 239R18 has a very good, probably what I think is one of the best snapshots of the what we're looking for in UHPC. What are the characteristics of this material that make it so special, and why is everyone so excited about it? So if you have a conventional fiber reinforced concrete such as GFRC, or even a high fiber content traditional concrete, you get this conventional kind of situation with your tensile behavior, right? So it will take the strain up to a certain point, to this point A, and then you have a very rapid softening reaction to where if you were to pull apart in direct tension, you had a coupon of this material with your fibers, aligned in random patterns and stuff. You pull this on this coupon, you'll develop traditionally you will develop one or sometimes two cracks, but then very soon a single crack will form and you'll be able to pull this material apart, and that's where this rapid softening occurs. With ultra high performance concrete, you get what we call strain hardening, to where the first cracks occur about A, but then you develop additional resistance to that tensile force. You develop multiple small cracks, and before you finally get a yield, and you develop that softening after that. So architectural concrete, architectural UHPC is, has to conform to the same UHPC behaviors. And just like all UHPC, fibers are going to be the key. If we don't have the fibers, then our material will be brittle, just like any concrete. So it's very important that we have fibers in there. If you're doing a structural application, steel fibers have been and will be going into the future the preferred material to put into your UHPC. They give you a lot of good tensile performance and that strength hardening performance. And the key is to get the right amount of fibers in there, and then of course the right geometry of the fibers. You want them to be small enough that you can get a heavy loading of those, and you get a lot of fibers per cubic yard or per cubic meter in your concrete. Fiber selection, of course, for architectural applications is very important, and we will tend to go with a non-metallic fibers tend to be preferred for architectural UHPC. There are applications where stainless steel fibers have been used to good effect as well. And so the idea is that you don't want your fiber to corrode and then stain the exterior of your concrete typically. So the thing that's gotten architects very excited about using UHPC is its ability to do very complex shapes We can have very thin sections because we don't have to worry about covering the steel, so to speak. So you can use UHPC with traditional, what we would call macro reinforcements, traditional rebar. I'll show you some examples of that. When you do use those traditional rebar, you can very much reduce the coverage on that because UHPC is essentially impervious. There's very, very little permeability with this material, very little egress of anything that would attack or cause the steel to rust out. And so the architects have learned this and they're understanding it. So they're doing these very complex shapes, very thin wall panels. They're doing these panels that have a large amount of voids in them. There's quite a bit of this out in the market. The architects are really embracing this, but we're also seeing applications that really make sense for what we would call, traditional architectural precast, where you do, for instance, sandwich panels. Sandwich panels have been around for decades. They're very energy efficient. They're really a very main frame. They are a meat and potato kind of a material for architectural precasters, especially in the North, Canada, northern U.S. Sandwich panels are pretty much the standard. There's a very good paper out, and there's very good research done by the Canadian Precast Pre-Stressed Concrete Institute, done with the Canadian Society of Civil Engineers, that has some very good detail on these sandwich panels. You can get a very thin white on the face of your sandwich panel that's got a pretty color on it, and then you can back it up with something a little bit heavier, a little bit thicker, and you can get those whites to react together, so you can transfer the loads through the foam depending on the ties that you have in between them. That's something we still need to develop, and I encourage everyone to look into that, because we still need a more efficient, easier to use system that'll tie these materials together. So as I said, architectural UHPC, as you would imagine, will be dependent upon a white Portland cement type materials, very light colors, so that you can get the color that you want in your architectural UHPC. If we have a very dark color, it's a challenge to get a light finish out of that, of course. So you can see these are the kind of strengths that you're looking for on the flexural strengths, and of course, like everything else, you want it to be a very attractive application. So the key placement advice with this material in the hardened properties, you just saw the hardened properties. It's very strong. It has very good hardened behaviors. When you're batching this material, you'll have to typically use a planetary or a horizontal shaft mixer, a mixer that has very high energy. A drum mixer is difficult to use. There are some mixes out there where you can use drum mixers, but traditionally most UHPCs, you need a high shear type mixer that can put a lot of energy into the mix. The finish on the face of the form is going to be very, very clean, very smooth, a very precise reflection of whatever the form liner is, or the form that you have that you're casting into. It will mirror the face of that form very, very accurately. The back might be a little tricky, so you want to make sure that you can use a screed, a motorized screed, or you can use other materials that help you keep that back open, and you can use finishing aids and those kind of things. But typically the back of the panel is not going to give you that nice clean kind of surface like you would get with like a broom finish on a precast. So these are one of the things that, if you're familiar with UHPC on highway work, you'll see that it tends to be a very thick thixotropic type mixes, but certainly UHPC can be a high flow mix. And with architectural applications, they're often these very high flow mixes where you've got a lot of rheology to work with. So you would typically want to back these up with a back form if you're going to be casting something very thin. Did I somehow get muted there, guys? Sorry.
Yes.
That's not what I wanted. So what I was saying is that you can see the rheology for an architecture will typically be pretty high, where you want a high flow. And that's the idea behind here, is that it doesn't have to be a very thick application like you would maybe get with like a highway application where it's where you want it to be a stiff mix. You can have a very high flow mix. One thing to try to protect from is the back of your forms. Make sure that you protect those from developing what we would call an elephant skin or dehydrating, right? You want to use a finishing aid, or you can even use misters to protect that. On a highway application, you would get cure on it right away. In your if you're doing architectural, typically you'll just make sure you use a finishing aid. One of the things that architects really like about this, you can see these are panels, are precast panels. That's a very popular application for architectural UHPC. You can see how thin this panel is with these. They've got these ribs that make it stiffen up the section and make it a little bit easier to make sure that you don't have to worry about the thing flexing or otherwise developing any cracks. Obviously, like we talked about, this material would hold together. You wouldn't have to worry about it falling apart or anything like that. But you still may have a crack if you warp it too severely. So a good strategy is to put in some stiffening fins like you see here. These very thin sections are possible because of our very high tensile strengths and the flexural strengths that you can get from those members. Blast resistance is a really neat application for UHPC, and you can make it look beautiful and have it be an architectural finish that also has blast loading or blast ratings. So the Paddington Station in the UK, it's got 37,000 square feet of this architectural UHPC, and you can see how most of the panels are, I should say, quite a few. I would think it's at least half or 3/4 of the panels have this perforated look to them, and they use that for all kinds of stuff. It helps with the acoustics. It helps with, they actually use fenestration in some of those behind those panels. So these are examples of what can be done if you take advantage of the blast resistance. In North America, the big applications for architectural UHPC tend to be solid panels. They can be very thin. Of course, when you're very thin, you can be much lighter. The material is extremely durable, and you can get these really dramatic finishes. Hats off to Tactile. Our colleagues up in Turtle Creek, Pennsylvania, have really done a very good job of introducing these materials to the market. You can see some of their, the finishes they can get on the face of these panels. Another good company that's able to do this is Envil Facade out of South Bend, Indiana. They've got another example you can see. So architects are seeing this, and they're really embracing the idea of using these rain screens, or they call them out, all these facade panels, in many different ways, but they can really look beautiful. You can hide the tiebacks, you can secure them to the wall, so there's no visible connection, but it's a very durable finish. You can also, of course, design it so that there's a large section of voids. This is over 65% voids in these rain screens, these panels. These are, they have concealed tiebacks. You can see here up in the upper right, they've got these standoff connections to the wall. These are cantilevered out, and because you don't have, you have these large voids, you don't have as much weight, so you're able to design for that. These are the panels where they've used some traditional reinforcing. So there's some GFRP bars up in some of these corners up where there's might be a lot of load or a lot of stress around some of these openings, and so they'll put a few of those bars in there just to stiffen it up and protect this panel. You can see this panel is right here, is this corner of this great big circle. So, or this one right here is the bottom left of this big circle. So, that's the kind of applications where it makes sense to couple it with traditional reinforcing. So Hycon is, they did the last project that was just shown, and they did this one. Of course, they've been around the longest probably of any architectural UHPC producer that I know of. They were part of very early adopters in Denmark, where ultra performance was essentially invented back in the 70s and 80s. They came in shortly after in the 90s with a material called compact reinforced composite, which is a type of a UHPC. It's kind of their branded UHPC. And you can see this is just a really dynamic application. It's very simple, very high tech, very clean, a lot of beautiful lines there. That is, really dramatic and exciting for folks. They've done a lot of stairs. If you're interested in this, I would encourage you to look up this project, this Per Arsleff headquarters. And I apologize to anyone who knows how to say that right. I didn't say the name correctly, but you can see they have a single column here that goes up, and then the handrail follows the stairs around. It's a really dramatic use of ultra high performance concrete. So all this very thin stair treads, that's all architectural UHPC. These are formed in sections, and then they are cast in the field to join them together, right? So to connect the different sections, and they use an ultra high performance type mix for that connection. Balconies, of course, are everywhere in the world. Of course, everybody wants to step out on their balcony. These box balconies, you can see they're very thin. You can see the floors of these, they're very thin, and basically the roof of the one is the floor of the one above it. So it's a pretty neat application. You can also have your balconies be like a parapet where they're cantilevered out, and because the material is quite light, you're able to do this with this ultra high performance concrete. And of course, I don't want to have you think that architectural UHPC is only for precast. Cast in place architectural UHPC is certainly attainable. You can see this is the Cosmos Resort, Healing Stay Cosmos Resort in Korea. This is the formwork. So as you can see, the architects said, look, we've got this dramatic material, let's really push the limits. And so that's what they've done. This is an award-winning project. It's on the coast in Korea. And you can see each one of these different petals of this lotus flower design is essentially an apartment. And it's like an inn where you can go enjoy the scenery and the tranquility of the coast there in this really dramatic ultra high performance concrete structure. So I just encourage everyone to be looking for applications where ultra high performance can be used, and remember, it can be beautiful. You can do a lot of amazing things with it. And when we're using these materials, they're very durable, they're very resistant or resilient, and of course they last and last. So we're building for the future. We might as well make it look beautiful. And with that, I can take any questions that anyone might have.
Thank you, Larry. A big round of applause to you and your presentation. A beautiful pictures. Thanks for sharing all of this and putting this together. Very much appreciated. Impressive. Very impressive. So we do not have much time before we go to the next presentation, but there's one question I'd like to ask you about. Frank asked, can this UHPC be made in a ready-mix truck and at a 6-inch slump, or what would be the slump?
Depending on the mixture that you're using, they can be done in a ready-mix truck. Not typically, but there's a manufacturer out there, Steel-like, which is well known for being able to be used in ready-mix trucks. So that's something that can be done. And depending on the application, depending on your admixture load, that's certainly something that can be done. It depends on your application when that makes sense, but it's certainly possible. It's not traditional. It's not probably not the norm yet, but it is something that can be done.
Yeah, thank you. And then another quick question for you, Larry, in terms of the flowability of this mix. Someone asked if this is achieved by a higher dosage of superplasticizer, so they're wondering where this is coming from, and also compliment on your presentation. And the second part of this question, besides the superplasticizer, is the random orientation of fibers, how this is being taken into account.
Right. So yes, you can juice it up with Super Ps and get it to really flow. Those flows that you saw in the video when I somehow muted myself, you see a very high flow. The material will really lay down, so you get a very broad flow on your table if you're measuring it. The orientation question is this. So typically a random orientation or a preferential orientation is what we're looking for. If you're doing an architectural panel similar to the one that was early on in the images that I showed, showed the guys kind of reaching down and touching the material, you can start on one end of your pour and work your way across, right? So if I'm starting on this side of my panel and I go to where I fill the entire panel, let me start this way, start this way and come across, then I'm going to have preferential fiber orientation in that direction of the flow, right? Of how I cast that flat panel. If I'm doing a very tall, very skinny, or I'm doing a very elaborate, things like that, what you want is a random. You don't want it. You want to pour it so that you end up with a fairly random orientation, so that you don't end up with big seams. One of the things we want to avoid when we're casting is a joint, like a casting joint, because the concrete, the UHPC, will fill that all in. You'll never even see that there was a joint there, but the fibers will not transverse that joint. So try to cast it all at once. Even these big elaborate ones, try to start from one end and go to the other, and then your fibers will typically be where you want them to be. But that's a big part of that is in the actual casting and in the placement technique.